Hello, ladies and gentlemen. I am going to talk today about two problems, or at least one problem, see how far we go. The first problem is, in a way, the problem which begat modern probability theory. It goes back to about the year 1500, but the work on it was done in the 17th century, that is the 1600s. It's called the problem of the points. And I'm going to explain something about that problem. And we're going to provide one solution, but I'm going to explain two different approaches to the solution. Okay, so let me begin. So this is example 4J. I think I should pull it up. Okay, so here's the problem of the points. It's a classical problem in probability theory. It goes back to the 1600s. We're talking about independent Bernoulli trials. Whenever I say that fancy term, all I mean is you're doing an experiment with one of two outcomes. Think of flipping a coin, and you consider it a success if you get heads and a failure if you don't get heads, you get tails. So let's assume the coin is not necessarily a fair coin, so the probability of heads is P, or the probability of success is P, and the probability of failure is therefore 1 minus P. And you're going to do this experiment over and over. So you start with two players, let's say player A and player B. Player A gains 1 point when a success occurs, and B gains 1 point when a failure occurs. The first failure to win, say, T points, T is some number, wins the game. Suppose that the game is stopped for some reason. At the point of stopping, player A has won, say, A points, lowercase a, and player B has won lowercase b points, where both A and B are smaller than the amount you need to win. So the question is, how do you divide the stakes of the game? So the equivalent problem is, and this is sort of easier to formulate mathematically, what's the probability of player A winning at least n points of n plus m minus 1 points total? I'm sorry, of n plus n minus 1 points of the next n plus m minus 1 points, where n is t minus a and m is t minus b. So that's the question, and we're going to call that probability PNM. So what's the probability of winning at least n points in the next n plus m minus 1 points? Okay, so and the reason why you're looking at n plus m minus 1 is because n is t minus a and m is t minus b. If you add those together and subtract 1, well, ignore that statement. Let's just look at this part of the problem, this last part. That's what we're interested in. Okay, so let me save the problem and let's move on and solve it. Okay, so I should have said at the very beginning that I'm not going to demand that you know how to do this. This is meant to be more of an illustration and background. What we're going to be doing today is much more calculationally intense than what we've done up until now. I think it's important that sometimes we do problems you're not going to be tested on. Okay, so where are we? So we're talking about P of n comma m, and this is the probability of at least n successes before making m failures. So that's actually a way to formulate what was on the last slide, the probability of at least having n successes before m failures. In other words, you have the game stops and you want to say, aha, let's continue the game and keep playing, and I want to make n successes before I make m failures. And so there are two approaches to computing this number. And this is the problem of the points is computing this number. So one approach is due to a philosopher called Pascal. So if you've taken a philosophy course, that name would probably arise. He was a French philosopher. And it goes like this. P and M is equal to what? Well, suppose you have made n minus 1 successes. Before you've made m failures, and you play one more time. So if you win, you'll have n successes. But what is the probability of winning? Well, let's say the probability of winning is p. The probability of success is p, we said. So if you win again, you'll have p, and that's one way to make n successes, okay, before you make m failures. There's another way to do it. Namely, we could have made n successes and m minus 1 failures, and we play again, and if we fail, we've still made n successes. If we fail, we've still made n successes before we've made m failures. So these are the two possible ways of getting to n successes before obtaining m failures. So this is called a recursion. It's called a recursion or iterative formula. And there's also some initial conditions. To this. If you've, it turns out that if you think about what this means, Pn0, the probability of making at least n successes before making 0 failures is absolutely 0. And the probability of making no successes before making m failures is exactly 1. Because if you've made right, so these are the initial conditions of the problem. Okay, so this is the book basically points this out, that this is called a recursion relation or a recursion equation. And there are methods of solving this that I don't want to go into, but this can be solved using various techniques, which you probably don't know, and some of you may have seen this, something like this, but I'm not going to go into it. So the book concentrates on the second solution, which I find to be much easier to deal with. So the idea is to consider the following thing. What's the probability of having k successes in m plus n minus 1 trials? Well, so you have m plus n minus 1 slots. These are the trials. And you want exactly k successes in that. So how many ways can you put the successes in? You can put the k successes in m plus n minus 1 choose k ways. So here would be success, here would be a success, let's say, and the rest would be failures. Now, what's the probability? Well, if you have k successes, that contributes a p to the k. And the remaining cases are failures. The remaining slots are going to get failures put in. And how many are there? Well, it's going to be 1 minus p to the number of them is the exponent of 1 minus p, which is n plus m, or m plus n minus 1 minus k. So that's the probability of k successes in m plus n minus 1 trials. So that means that the probability of at least n successes in m plus m minus 1 trials. By the way, this is the same thing as at least n successes in n plus m minus 1 trials. Because if you have at least n successes out of n plus 1 things, the remainder of things can never be is always smaller than m. Okay, so if we now take this number here, we want at least not k successes, we want n successes or more. That means we have to sum. K goes from n to n plus m plus n minus 1, p to the k, 1 minus p. Oops, there's also the binomial coefficient. And this is the formula that solves the problem. So so that's the problem of the points. Good. Okay, so I'm going to move on to the gambler's rune problem, which is about betting. So let me pose the problem. I'm going to put it on the screen. So in this problem, you have two gamblers, A and B, and they're betting on the tosses of a biased coin in which the probability of heads is P. So if on a flip the coin is heads, A wins and collects $1 from B. If it comes up tails, then B collects $1 from A. The play continues until one of them runs out of money, or not. Assume A starts with I dollars and B starts with, say, N minus I dollars. So the total number of dollars in the game is N. What is the probability that A ends up with all the money? So that's the gambler's rune problem. And I'm going to formulate it right now, mathematically. Okay, so let E be the event that A ends up with all the cash, assuming A starts with I dollars and B starts with N minus I dollars. Okay, I'm going to set P, the probability of E, which is what we want. I want to rename the probability of E to be P sub I, because it's going to depend upon how many dollars A has to begin with, right? And that seems reasonable because if A starts off with $1 and B starts off with $1 billion, well, it's very likely A is not going to win. Okay, but if A starts off with $1 billion and B starts off with $1, it's likely that A will win. Okay, so assuming you have a fair coin, let's say. So so now I want to compute P sub I using the law of total probability. That's P of E, as we said, and that's given by I want to define a new event, H. Let's define an event H here. H will be the event that the first flip is heads. The first coin flip is heads. Okay, so what is P of E? It's P of E given H times P of H plus P of E given H complement times P of H complement. Now, I want to compute what that is. So now what's P of H? P of H is P, and P of H complement is 1 minus P. Now what is P of E conditioned to H? Well, that means that at the start of the game, the very first flip, A wins. So he collects $1 from B, which means that A is starting with I plus 1. If we assume now and think, let's start the game now after the first flip, that means A has one more dollar in his hand, and B has one less dollar in her hand. So in other words, P of E conditioned to H is P I plus 1. So it's Pi plus 1, and this is an uppercase P I want it to be, times P plus, okay, so what is P of E conditioned to H complement? By similar reasoning, this would be P of sub I minus 1. A starts off with I minus 1. Okay, so that's it. And moreover, what is P sub 0? P sub 0 is the event that A ends up with all the money, assuming that A starts with $0. Well, that's obviously going to be 0. And we also know that if A starts off with all the money to begin with, and B has no money, A is always going to win. So these are the initial conditions. Okay, so I want to clear the screen and rewrite these conditions in the following way. Before I do that, though, I want to set Q equal to 1 minus P. Okay, so I'm going to do that too. Okay, all right, so let me clear this. So I've just placed up at the top of the whiteboard the equations. Okay, now if you take this top equation, you can rewrite it in the following way. See, P plus Q is 1, so because Q is defined to be 1 minus P. So you can think of it as P plus Q times Pi equals P times Pi plus 1 plus Q times Pi minus 1. Now, I'm going to get the like terms on the left together. So I'm going to think of this as P sub I plus Q P sub I equals P sub I plus 1 plus Q P sub I minus 1. Now you can reorder the terms in the following way. You can get the two terms involving the lowercase p together, and you'll get P times Pi plus 1 minus P sub I equals Q times Pi minus Pi minus 1. Okay, and if you want to, you can divide both sides by P. I'm assuming P is not 0 when I do that. And this equation appears. And it's this equation we're going to work with. It's equivalent to the original equations, the original equation we started with. Okay, so what I'm going to do is I'm going to take this and start writing down various cases of it. But to do that, I need space. So I'm going to clear the screen. Okay, so let me start writing down that equation again. So what did it say? It said that pi plus 1 minus pi equals q over p times pi minus pi minus 1. So what does that tell me? It says that let me see. So if we looked at p2 minus p1, that should be q over p times p1 minus p0. I'm taking the subscript to be 1 over here, I to be 1, and this is the first case of that equation in the box up here. And because p0 is 0, this is the same as q over p times p1, because the p0 term goes away. Okay, we have also p3 minus p2, and that's q over p times p2 minus p1. But we know what that is because we know that p2 minus p1 from the previous line is q over p p1. So you get q over p squared times p1. Well, I think you probably from this see the pattern. There's going to be a pattern. Pn minus pn minus 1 is equal to q over p to the power of n minus 1 times p1, and these are uppercase things. Okay, so so that's what we get, and what I'm going to do is I'm going to add up the first I terms on both sides. Why am I doing that? Well, you see, when I add the P2 minus P1 to P3 minus P2, the P2s cancel and they go away. And likewise, every time I add something, everything except the outer terms cancels. So what you're going to get is Pi minus P1 if I add the first I terms on the left. And on the right, you get something sort of interesting. You get, you're going to get an expression of the form Q over P. Let's set X equal to Q over P. So you're going to get X plus X squared plus X cubed all the way up to X to the I minus 1. And that's going to be multiplied by the number P1. Okay, so so that's the equation you get, and from doing that. And let's see. So now what I can do is now bring P1 over to on the left side over to the right side, and factor out the P1 from both sides, and you see that Pi is equal to 1 plus X squared all the way up to X to the I minus 1 times P1. Okay, so now what does that tell me? That's the same thing as, now this is something you learn in Calc 2. The sum of these terms is 1 minus x to the power of I divided by 1 minus x, at least if x is not 1, and times P1. Okay, so actually this formula only works if x is not 1, and if x equals 1, you got to do something else. You just substitute x equals 1 into the equation, and you'll see that Pi is I times P1, and Pi is I times P1 if x equals 1. So let me rewrite what I just wrote in a different way so that it's clearer. So what am I saying? I'm saying that summary so far, P sub I is equal to 1 minus x to the I over 1 minus x if x is not equal to 1, and if x equals 1, it's equal to I times P1. Now, let me point out, what does it mean for x to be equal to 1? So x not equal to 1 means that P over Q is not equal to 1, which means that P is not equal to Q, which means that P is not equal to 1 minus P, which means that 2P is not equal to 1, which means that P is not a half. So this case really means P is a half, and this means that P is not a half. Oops. Okay. All right. So what about now? What about this formula is good for all I. So if we take the case I equals n, notice what this says, because P sub n is equal to 1, we saw that was an initial condition. So we see that 1 is equal to 1 minus x to the n over 1 minus x if P is not a half, and it's equal to n times P1 if P is a half. Okay, so what I can do then is, oh, and there's a P1 here. I left it out. There's a factor of P1 in the first term. What I can do is rewrite this equation in the following way. I can solve for P1 because 1 is equal to this expression times P1. Well, what does this tell us? So this tells us that P1 is equal to 1 minus x over 1 minus x to the n. Notice I've taken the reciprocal because I'm solving for P1 if P is not 1/2, and it's equal to 1 over n if P equals 1/2. So I got what P1 is. Okay, but if I got what P1 is, let me circle that, and I know what PI is, in terms of P1, I can substitute the P1 into the top equation, substitute the value I got for P1. So let me write out what that is, and I'm going to summarize again now. So if you follow where I am so far, this tells us that PI is going to be equal. So what I do is I substitute the value I got for P1 into the equation for PI, and this is what pops out. It's 1 minus x. Well, I'll write x as Q over P for now. No, let me write it as x. X to the I over 1 minus x to the n if P is not a half. And if P is a half, I write it as it becomes I over n. Okay. So that is what PI is. Okay. So now let me stop here for a moment and note the problem has a certain symmetry. Suppose we let QI be the probability that B ends up with all the money, assume if A starts with I dollars. Okay, so excuse my handwriting. And B with n minus I dollars. Well, we could have done the same exact analysis, except the rules of P and Q. See, X is P over Q here. And you see that you get the same exact formula for Q sub I, except the rules of P and Q are interchanged. and the roles of I with n minus I are interchanged. So Q sub I will be 1, let's set y equal to Q over P. So it's 1 minus y to the n minus I over 1 minus y to the n if Q is not a half. By the way, Q is not a half if and only if P is not a half. And it's going to be given by n minus I over n if Q equals a half. Okay, so you can take these two expressions that I'm boxing off now. And the remarkable thing is it's simple algebra to check that these two expressions imply that Pi plus Qi equals 1. Okay, this is just plain old algebra. It's tedious algebra, but what this is telling us is something amazing, or not amazing, but it tells us what is Pi plus Qi. Well, there are two events. The first event is A ends up with all the money if A starts with I dollars. And the other event is that B ends up with all the money if it starts off with I dollars, right? And this is telling me that in either case, because that's what the plus is, it's the event. If we take the two events that give Pi and Qi, those are complementary events. And it's telling me that Pi plus Qi is 1. So it's telling us with probability 1, either A wins, will end up with all the money, or B will. Now, this is not absolutely obvious, because you could imagine a scenario where two players are playing forever and the game never stops. And what this calculation shows you, with probability 1, with absolute certainty, with probability 1, the game will stop. One of the players will lose the money. So it's probability 0, the game. In other words, it's probability of 0 that the game will never terminate. The game terminates with probability 1. So that is really what this is all about. That's why it's called gambler's rune. One of those gamblers is going to lose with probability 1. Okay, so I hope I didn't mangle that too much, but I wanted to give you a flavor of this. Is actually, historically speaking, the problem which gave rise to modern probability theory as well, or one of them, one of the two. So the other one was the problem of the points, and there's this problem. These two both played a role in the development of the subject. So have a good day.